If you've ever been online, peacefully browsing the safe, respectable corners of the internet, you've probably never thought about the math quietly working behind the scenes to keep your digital life from going up in smoke. Because while that sketchy pop-up you almost clicked and the shady email attachment titled invoice.pdf.exe might look harmless, it's often the firewall standing between that click and your entire network becoming part of a Russian botnet. Firewalls don't stop you from making bad decisions, but they can stop those bad decisions from phoning home, opening backdoors, or spreading across your network like digital wildfire. And believe it or not, it all comes down to math. But what is a firewall anyways? A firewall is a network device or system that blocks unwanted traffic and permits wanted traffic based on a defined set of security rules. Now, when most people think about firewalls, they usually think about host-based firewalls, like Windows Defender. But you can actually bucket firewalls into 5 different types. The first type are host-based firewalls. These are installed on individual devices and control app or port-level traffic for that device. An example of a host-based firewall is Windows Defender. The second type are router firewalls. These are built into home or single office home office routers and perform network address translation, or NAT for short, and basic stateful filtering. NAT essentially just hides your internal devices behind a single public IP address, and stateful filtering monitors active connections to decide whether incoming traffic is part of a trusted session. Examples of router firewalls can be seen with ASUS, Netgear, and TP-Link routers. The third type are next-generation firewalls. These are advanced network firewall appliances that include features like deep packet inspection, which analyzes the actual contents of network packets, intrusion prevention systems, which detect and block known attack patterns, and application-level control, which lets you allow or block traffic based on specific apps like Facebook, Zoom, or BitTorrent. Examples of next-generation firewalls can be seen with Cisco, Palo Alto, and FortiGate firewalls. The fourth type are cloud firewalls and live inside cloud platforms. These types of firewalls control traffic to and from cloud-based resources. Examples of cloud-based firewalls include AWS security groups and Azure NSGs. The fifth type are virtual firewall appliances. These types of firewalls can act like next-generation firewalls, but are deployed in virtual or hybrid environments. Examples include pfSense, OpenSense, and Palo Alto VM series firewalls. So whether it's a host-based firewall, a router at home, or an enterprise-grade next-gen firewall, they may look different on the surface, but under the hood, they all boil down to one core idea: rule-based access control. This is what rule-based access control looks like behind the scenes. In technical terms, this kind of table is called an access control list, or ACL for short, and it's the foundation of how most firewalls make decisions. Each rule is essentially a simple test: who's sending the traffic, where's it going, what protocol and port is it using, should we allow it or block it? On the surface, these rules might just look like a bunch of rows and columns, but behind that table lies something deeper: the mathematics of decision-making. Specifically, the concepts of set theory and logic, which come from a branch of math called discrete mathematics. Wait, math? And while that might sound intimidating, it's actually pretty intuitive once you see how it works. When it comes to set theory, there's 3 key ideas you need to understand: set memberships, set operations, and set partitions. And by the end of this video, you'll understand what all of these symbols mean. When it comes to logic, we'll focus on and or conditions, not statements, truth tables, and if-then rules. These tools are what make firewalls work under the hood, turning technical rules into mathematical logic. Once you understand how firewalls make decisions using math, you'll not only be better at configuring them, but you'll also be better at thinking like a firewall. So let's start with set theory, the foundation of grouping, matching, and controlling what gets through. But what is a set? A set is defined as a collection of objects that are referred to as the elements of the set. Within a set, you have elements which can be anything, such as a letter, an exclamation point, a $sign, or even a smiley face. Each set has a name, so in this case, set A would have these elements within the set. Set membership lets you know who belongs in the set, and is written with this E-looking symbol. You write it like this, and this means A is in set A. Now let's say you had a set with the name of A, and it had the elements of 1, 2, 3, 4, and 5. If you wanted to define a new set X that only has elements of A greater than 2, you would use what's called set builder notation, and it would look something like this. And this reads: pick each element X from A, and only include it in the new set if it is greater than 2. In this example, X is a variable representing the elements from set A that satisfy a condition. Now let's look at some example code in Python. Now, firewalls, like the one Cisco uses, don't use Python or literal sets, but the logic they follow, with matching IPs, combining rule conditions, and evaluating access, can be modeled this way to better understand what's happening under the hood. Plus, Python is probably the easiest language to read if you're new to programming. So we have Python code here to exemplify set membership, And as a reminder, the example we had is set A, which contained these elements, and we wrote down set membership with the notation of lowercase a is in set A. This is what this notation means. So we want to replicate that in Python. So we have a set here, and if you're new to Python, when you write it with brackets, this is actually called a set as well. So we have a set here of allowed IPs with 3 elements, which are IP addresses. Have a simple function here, check allowed IP. That'll take an IP address as a input. So if the IP address is in the set of allowed IPs, it'll print the IP address is an allowed IP address. And if not, it'll print IP address is not an allowed IP address. So calling the function here, check allowed IP, we have 10.0.0.6. And as we can just do a quick scan, it's not within the set of allowed IPs. So running it, we'll get 10.0.0.6 is not an allowed IP address. But if I switch it to .5 and then run it again, we'll see that it prints out 10.0.0.5 is an allowed IP address. So this is just a quick and easy example exemplifying set membership in Python. Set operations are mathematical operations that combine, compare, or relate elements of sets. The 5 main concepts of set operations to understand in the context of firewalls include unions, intersections, differences, symmetric differences, and subsets. Unions combine elements from 2 sets, creating a new set with no duplicates. You write it with this U symbol. For example, let's say you had set A that had the elements of 1, 2, and 3, and you had a set B that had elements of 3, 4, and 5. A union B would contain the elements of 1, 2, 3, 4, and 5. To exemplify unions in Python code, we have this example as well. So going back to the example, we had a set of A and B, and A union B just combines all of the elements in both sets, or however many sets you're putting together with a union. So in the Python example, I have 2 sets here, one set of internal users, which has these 2 elements, which are these 2 IP addresses, and I have a set of VPN users, which has 1 element. So I want to combine these using a union. So Python within the set data type has a built-in union function as well. So very similar to what we're studying with set theory. So creating a new variable of all allowed, we union internal users, .union, and VPN users. So it essentially just combines both of them together. And then printing all allowed, we get all of the IP addresses and all 3 elements from both sets. An intersection finds elements common to both sets, and you write it with this upside down U symbol. Going back to our previous example, if you had set A that had elements 1, 2, 3, and you had a set B that had elements of 3, 4, and 5, A intersecting B would contain the element 3, because that's the element common in both sets. So showing an example of intersection in Python code. So intersection just finds the same element within certain sets. So using the same example as we had last time, except I've added another element to the internal user set. So we have 3 elements in this set and 1 element in the VPN user set. So similar to union, there's a built-in intersection function as well within the set data type. So we have the variable shared users, and we intersect and find the intersection between internal users and VPN users. So it should output, because they're sharing 10.0.05 as the element, that's what it should output. And running it, and that is the intersection between these 2 sets. The difference between sets finds elements in one set but not the other, and you write it with a minus sign. Using the previous example of set A and B, if you had A difference B, it would contain elements 1 and 2, because you're essentially saying what elements are in A that are not in B, which are 1 and 2. If you had B difference A, then it would contain elements 4 and 5, because you'd be saying what elements are in B that are not in A, which are 4 and 5. So to exemplify the difference in set theory using Python, once again, we have the same sets. Now, the difference finds essentially what elements are in one set that aren't in the other, and depending on which one you write first is the one that will be the new elements in the set. So for example, A minus B shows the difference of what's in A and not B, and B minus A shows what's in B but not A. So going back to our same Python example, we have this set of internal users and VPN users. So if we only want to find the internal IP addresses, we'll do internal users dot difference and then VPN users. And difference is again a built-in function for the set data type. So this is essentially the same as A minus B, because we're trying to say, okay, what's in internal users that's not in VPN users. And so printing this out, we'll get these 2 elements the 192.168.1.20 and the .10 because they're in internal users and not in VPN users. The symmetric difference finds elements in either set, but not both, and can be written with this XOR or triangle symbol. For our examples, I'll be going with this XOR, since that's how it's often referenced in computer science. Going back to our example, A XOR B would contain elements 1, 2, 4, and 5, because those are the elements in either set, but not both. So to exemplify symmetric difference in Python, I have this code, and once again, symmetric difference finds the elements in either set, but not both. So we have the two sets here again. I've added a couple more sets to VPN users. So this would be used to find exclusive IPs. So just taking a quick scan, we can see that they share 10.0.0.5. So the symmetric difference would include these two and these two because they're in either set, but not both. So internal users.symmetric difference with VPN users would be the exclusive IPs, and printing that out, we do get the 192.168.1.10 and the 20, and we get the 10.0.0.6 and the .7, and these would be the exclusive IPs, exemplifying symmetric difference. A subset checks if all elements of one set are in another, and is written with this rotated U symbol with an underline. For example, if you had set A that contained the elements 1 and 2, and set B that contained the elements 1, 2, and 3, then A subset of B would be true, because the elements in set A are within set B, making A a subset of B. So to exemplify subsets in Python code, we have this example, and once again, a subset just essentially checks if one set is part of another, and it has to be the entire part. So for example, 1 and 2, which is set A, is part of set B because it's 1, 2, and 3, so it is a subset. So back to the two sets, we have internal users and VPN users. So I'm combining some concepts here. So I do internal users.union with VPN users. This will combine all the elements together into one new set. In this case, it will be all allowed users. So all allowed users would contain all of the elements. So if we printed VPN users, if we wanted to check whether VPN users is a subset of all allowed users, this is the code. And this should print out true because VPN users, as mentioned, is all these elements, and so all allowed users is a set that includes internal and the VPN users. So printing this out, we get true, that VPN users is a subset of all allowed users. A partition of a set is a collection of non-empty disjoint sets whose union is the original set. Here's an example. Say you have set A, then a partition of A is a set of subsets such as A1, A2, all the way to AN. Now, to fulfill the definition of a partition, it must follow two rules. The first is that A has to be the union of all the sets, and that the sets are mutually disjoint. So let's say we have set A, which is 1, 2, 3, 4, 5, and 6. Let's say you have set A1, which has 1 and 2, and set A2, which has the element of 3, and set A3, which has the elements of 4, 5, and 6. So taking a look at sets A1, A2, and A3, you can see that the union of all these form set A, which is 1, 2, 3, 4, 5, and 6. And they are also mutually disjoint, meaning they have no element in common. So you would say set A1, A2, and A3 are not only subsets of set A, but they form a partition of set A. So here's a Python code example to exemplify set partitions. So going back to the rules of a set partition. So first is that, so the main set has to be the union of all the other sets or the subsets. So for example, in the previous example that we had, set A was the union of all the subsets, which were A1, A2, and A3. The second rule is that the sets are mutually disjoint, which means they can't have any elements in common. So looking at our Python code example, let's say we had the LA office, which has these IPs in it. And we had 3 departments, a marketing department, an HR department, and some guest users, all with IPs within their sets. So first I just created a departments variable that holds an array of all the departments. So it's the marketing, HR, and guest users. And then I created a department union. And this will help set us up later to check for the first rule. So first I do the marketing department and I union it with the HR department and then the guest users. So this department union holds all the elements of all 3 of these sets. So first rule is we have to check that Office LA is the union of all these sets. So to do that, I just created a simple function that set is union that'll take a subset union and the main set. So the subset union in this case would be the department union, and the main set will be the office, LA. And this function would just return true or false, whether or not they are equal to each other. The second function is to check for mutual disjointness. So the function is mutually disjoint. It'll take a parameter of sets. So first I just create a set array, just making sure that it is in array format. And then essentially what I'm doing here is I'm checking that the first department is disjoint with the second department. And then if it is, then keep going. And then check if the HR department is disjoint with the guest users department. And if it is, then it'll return true. If it returns false, either checking here or checking here, then it will return false overall. And these sets would not be mutually disjoint with each other. So finally, creating a variable is partition, and it combines these two rules. So the first checks whether the set is a union. So it looks at whether or not the union of all the departments is equal to all the IPs in the LA office. So that's the first rule. So that has to be true. And then we'll also check if all the departments are mutually disjoint. So as you can see, this is the first rule over here, and then this is the second rule over here. So running is partition. This should be true because if you just take a look, if you combined all departments, you would see that the union does equal every single IP in the office LA, and that they are all mutually disjoint. None of the sets share a common element. So running it, we get true right now. But let's say we changed one of the IPs in, let's say, guest user. So now this union of all the departments would no longer equal all the IPs in the LA office. So if we ran it, we'd get false because the first rule is false. If I change this back, now let's say the second rule was false, so that they are mutually disjoint. So that just means they would, and if they shared a IP address, it would be false. So let's say they share this, so that would be false as well. So changing it back to the original, the union is equal to the main set, and they are all mutually disjoint. Running it one more time, and it is true. So all these departments form a partition of the LA office in terms of IP addresses. And that just exemplifies set partition and how it can be used to group users by department or different policy zones. Now that we've seen how set theory plays its role, let's take a look at how logic, often combined with set theory, forms the core mathematical foundation behind firewalls. So what is logic? Logic is about deciding what's true or false based on clear rules. Logic is built around statements, and a statement is a sentence that is either true or false, but not both. For example, 2 plus 2 equals 4 is a statement because it's true. 2 plus 2 equals 5 is also a statement because it's false. I like Fridays is not a statement because it is neither true nor false, even though if it's true for myself. 3 minus x equals 12 is also not a statement because it is neither true nor false. The four main concepts of logic to understand in the context of firewalls include and or statements, not operators, truth tables, and if-then statements. And or statements are logical operators that help build compound statements. And statements are written with this upside-down V symbol and form a compound statement where both statements must be true. For example, 2 plus 2 equals 4 and 3 plus 3 equals 6 is true. 2 plus 2 equals 4 and I like Fridays is false. So to exemplify AND statements in Python, we have to remember that both statements have to be true in order for the AND statement to be true. So in the code here, I have two sets. The first set is allowed IPs, which holds elements of IP addresses. And then the second set is allowed ports, which I have ports 80 and 443. I have a simple function here called check traffic that'll take parameters IP address and port. And we're essentially just checking if the IP address is in the allowed IP set and the port is in the allowed ports, then print allow, else print deny. So running here, let's run this example, check traffic. So taking a look at this real quick, the IP address is within the allowed IPs, but this port number is not. So this should print deny, and it does print deny. If we were to put a port that is actually in the allowed ports set, then we should get allow. So as mentioned, for AND statements, both statements have to be true in order for the whole thing to be true. Or statements are written with this V symbol and form a compound statement where at least one of the conditions is true. For example, 2 plus 2 equals 4, or 2 plus 2 equals 5 is true. But 2 plus 2 equals 5 or 3 plus 3 equals 7 is false. So I have two sets here, the HR department IPs and marketing department IPs. So I have a function that just checks the IP address, and we want to know whether the IP address will be internal traffic or external traffic. So the function essentially just checks if the IP address is in the HR department IPs or the IP address is in the marketing department IPs, then print internal traffic. If the IP address is in neither of these, then it'll print external traffic. So essentially the IP address just has to be either in here or in here for it to be true. In this case, to print internal traffic. So checking it with 10.0.0.6, we can see it's in the HR department IP, so it should print out internal traffic, and it does. If I were to print an IP that is not in HR or the marketing department IPs, such as 10.0.0.8, then we should get external traffic, and we do. So that's an example of OR statements, where at least one statement has to be true in order for the whole thing to be true. The NOT operator reverses the truth value of a statement and is written with this symbol. For example, if A equals the user is logged in, then not A would be the user is not logged in. Here's a quick example exemplifying the NOT operator in Python. So we have a set of allowed IPs here and a simple function that is check traffic, and it takes an IP address. So essentially, we're just checking if IP address is not in allowed IPs, then print blocked IP is not in the allow list. So let's check traffic for 10.0.0.8 and take a quick look. It's not in the allowed IP statement, so it should print out blocked. And it does print blocked IP not in allow list. So that's an easy example showing the NOT operator. A truth table is a chart that lists all possible combinations of truth values for logical statements, so you can check if an argument is valid or see when a statement is true or false. Let's look at the truth tables for AND, OR, and NOT statements. Looking at the truth table for AND statements, if either one of them is false, then the compound statement is false. Let's start at the top and work our way down. If A and B are true, then A and B is true. If A is true, but B is false, then A and B is false. If A is false and B is true, then A and B is false because A is false. If A and B are false, then, of course, A and B is false. You'll notice that the AND statement is only true when both A and B are true. Looking at the truth table for OR statements, if either one of them is true, then the compound statement is true. Let's start at the top and work our way down. If A and B are true, then A or B is true. If A is true but B is false, then A or B is true, because A is true. If A is false and B is true, then A or B is true, because B is true. If A and B are false, then A or B is false. As mentioned, you'll notice the OR statement is true if at least one of A or B is true. Looking at the truth table for NOT statements, you just invert the truth value. So if A is true, then not A would be false, and vice versa. An if-then statement is a conditional statement that expresses a relationship where a certain condition must be met for a specific outcome to occur. If-then statements are written with an arrow like this, where if A, then B. Here is the truth table for an if-then statement. You'll notice that each condition is true except when A is true and B is false. Let's look closer at that with an example. For example, let's have A equal to the store is open and B equal to I'll buy milk. So if A is true and B is true, then if A, then B is true. And using our current interpretation, if the store is open, then I'll buy milk. If A is true and B is false, then if A, then B is false. And the interpretation would be, if the store is open, I won't buy milk. And there was a contradiction there, and a promise was broken, because the statement was, if the store was open, then I would have bought milk. Now, if A is false and B is true, then if A, then B is actually true. Now, the interpretation would be, if the store is closed, then I'll buy milk. Now, this is fine and there is no violation, but why? So unlike the one above, if A is false, in this case, the store is closed, and you still buy milk, maybe you went to another store. Well, you made no promise that you wouldn't buy milk if the store was closed. So there was no violation, and the statement is true. Now, if A is false, and B is false, then if A, then B is true. Because if the store is closed, then I won't buy milk. So to exemplify if-then statement in Python, we have this code. Now referring back to the table, only time it is false is when A is true and B is false, because essentially you made a promise on A, and then if B doesn't fulfill the promise, then it's false. So with the example we have here, we're going to be checking protocol and a port for HTTP on port 80. So we have a function check web traffic, which will take the protocol and the port, and we'll essentially check, the protocol is A in this case, and the port is B, going back to the example here in the table. So this would be false. So if protocol equals HTTP and the port isn't 80, then it'll print policy violation. So this is essentially the same as this right here, where if it's true, but the port is false, then it'll print false. Everything else will print traffic allowed. So for example, let's run through the top. So true and true would be when the protocol is HTTP and the port is 80. So if we run that, we get traffic allowed. Now, if we run HTTP and if we put in a port like 110, then we'll get policy violation. HTTP must use port 80. So this is the same as true here and false here, which gets the false essentially in this example. So that's the example of an if-then statement. And that's it. That's the math behind firewalls. Thanks for watching.